Hey Chem Kids, Campbell here. Today we're going to talk about how trendy the periodic table is. So you're going to need your periodic table again. So if you don't have it out, pause the video and get it out. So on the periodic table, right, everything that's in the same period or row, right, has the same outer energy level, and everything in the same group, which is the column, right, has the same number of valence electrons. So the trends in the periodic table vary in a very systematic way. The trends we're going to talk about today are atomic radius, or like the size of the atom. We're going to look at neutral atoms and ions. We're going to talk about ionization energy and electronegativity. Those two are kind of similar ideas, but, well, really the exact opposite. And then we're going to talk about how reactive metals and nonmetals are. Let's talk first about size. Size matters, right? Atomic radius, what it is the distance from the very center of an atom's nucleus to that outermost electron. So it's kind of like how big it is. Now, what's interesting is as we go across the periodic table, as we increase our number of valence electrons, the atoms actually get smaller. So we'll have to talk about why that is. Now, as we go down the periodic table, the atoms get larger. Now, that should make sense, right? Because every time we add another energy level, right, and adding more electrons to that energy level, it gets bigger, right? That makes sense. As we go down, the atoms get bigger. And you can see that with lithium, sodium, potassium, right? They're all getting bigger as we go down. But why do atoms get smaller as we go across? Why is lithium, which has less protons and less electrons than neon, why is it bigger? Well, the crazy thing is that as we add electrons to that same outer energy level, so staying in that same row, the number of protons also increases, but protons and electrons have opposite charges. So while we're adding more electrons to the same shell, so the same distance, those protons inside are pulling tighter and tighter and tighter on those electrons. And because as we add protons, we add the attractive power of the nucleus, it actually shrinks the atoms and it makes them smaller. Pretty interesting. But something you're probably going to have to remember because it seems counterintuitive. Now, ions are a little more logical. Right? Cations, which are the losers of electrons, right? Cats are losers. They actually get smaller, and that makes sense, right? If you lose mass, you lose weight, right? You're getting smaller. And so you can see that here here's lithium. When lithium becomes +1, right? It shrinks. Makes sense. Loses weight, gets smaller. In fact, the more electrons you lose, the smaller and smaller you get. So if you look at the difference between lithium, which is +1, and lost 1 electron, beryllium, which lost 2 electrons, and boron, which lost 3 electrons, look how tiny boron is compared to lithium. That makes sense, right? And then for our anions, right, the anions actually gain electrons. They get larger. So we can see that as nitrogen acquires electrons, it gets bigger. And of course, the more electrons you acquire, the bigger you get. So that's why nitrogen is bigger than oxygen, which is bigger than fluorine, since fluorine only gained 1 electron and nitrogen gained 3. So that makes sense, right? Let's talk about ionization energy. Ionization energy is the energy needed to remove an electron from an atom. So they don't just go away. You actually have to kind of rip them out. And so lithium, which loses an electron to become +1, right? It loses it because it's got just 1 in that outer shell, and having a full outer shell is more stable. So it doesn't just say, hey, go ahead, take that electron, I don't want him. You actually have to pull him out. And so that takes some energy. Now, the thing about ionization energy is as you go across the row, the ionization energy increases because those protons, the more protons you add, the more they're pulling on those electrons, right? So it takes more energy to rip them out. And remember that all atoms want to get 8, right? They have noble gas envy. So the closer they are to 8, the harder it is to pull those electrons out. As we go down a column, though, the ionization energy decreases. Because, hey, by then they got so many electrons, right? The more shells they have, the more electrons they have. The farther away from the nucleus they are, the less the attraction is. It's like a long-distance relationship. It's like, hey, whatever. So it doesn't take as much energy to pull an electron out when you get down to the bottom of that periodic table, because there's so many electrons there. Puff, what's 1? So ionization energy is the energy to remove an electron. So highest ionization energies are in that top right corner. Now, if we take a look visually, a little bar graph here, you can see that the metals, right, the metals have a pretty low ionization energy, right? They want to be positively charged. They want to have an outer shell of electrons, so it doesn't take as much energy to get an electron away from them. But if we go to our nonmetals, and especially those noble gases, which already have 8 electrons in their outer shell, whoa, they are holding on tight, man. You got to be strong to pull one of those electrons away. So it takes a lot more energy for nonmetals, so they have higher ionization energies. Now, electronegativity is like ionization energy, except remember I said it's like the exact opposite. Electronegativity is how attractive an atom is to an electron. So we call it the electron attracting power of an atom. As you can imagine, the ones that are closer to 8 are much more attractive than the ones that are here and far away from 8. So as we go across a row, just like ionization energy, electronegativity increases. Now you'll notice something missing from this. The noble gases are not here because the noble gases are not attractive at all. They don't want an electron at all. So they're not even on our little chart. Now, of course, there are some variations when you get into sublevels here. You can see that between copper and zinc. Zinc's actually less attractive than copper is. So there are some variations there, but you can actually find the values for electronegativity on your periodic table. Oh, makes it easier on the test. Now, as you go down a row, right, as we go down energy levels, it actually decreases, right? When you got so many electrons, you're like, hey, dude, that's okay. I don't need any more. So you're not as attractive the bigger you are. So on the periodic table, you can see that. In fact, the range of electronegativity is the very smallest. So the least attractive here is francium and cesium. And the most attractive, the hottie in the periodic table, is fluorine up here at 4. Our last trend is on activity, or really it's reactivity. And what it is how reactive an atom is. Now the crazy thing is, it's exact opposite for metals as it is for nonmetals. For metals, as you go across a row, the reactivity decreases. So our very first column, the alkali metals, are much more reactive than the alkaline earth metals, which are more reactive than those transition metals. So sodium, which is right next to magnesium, sodium is much more reactive than magnesium is. In fact, it can be a little explosive. Whereas magnesium, we lit it on fire in lab. We wouldn't do that with sodium. And as you go down a column, it gets even better. Francium is incredibly explosive. The alkali metals in general are explosive, but francium, so francium is much more reactive than something like lithium, which is higher up. Now you should have noticed that in the alkaline earth metal lab, that as we went down, our calcium was much more reactive than our magnesium was. So you should have seen that in lab. So metals, the most reactive, is down in that very bottom corner where francium sits. So reactivity in metals goes like this. But in nonmetals, it's the exact opposite. As you go across a row, reactivity increases. So fluorine is much more reactive than something like carbon. In fact, the halogens, which are in that second last column, are pretty darn reactive. And in fact, as you go down that column, it actually gets less reactive. So fluorine, so for metals, up in that top corner where fluorine is, that's how reactivity increases. Now, one thing that's not there for reactivity is the very last column, our noble gases. Noble gases, remember, they have 8. They don't do any reactions. That's why it took them so long to find them. So when we talk about reactivity for nonmetals, we're leaving out that 8th column there, the noble gases. So the halogens in the nonmetals are the most reactive. One of the halogens, chlorine, which is right there underneath the fluorine, chlorine gas is very toxic, very reactive. Bad stuff. All right, so on your periodic table, this is what I want you to do. I want you to make these arrows. So up at this top corner, in the periodic table, we have increasing ionization energy. So this one actually does include column 8, our noble gases. So make arrows that point up to the top corner and write increasing ionization energy, increasing electronegativity. So these things, it takes more energy to pull an electron out. They're much more attractive to electrons, except column 8 for electronegativity. And also this corner is the highest in nonmetal reactivity. So ionization energy, electronegativity, and nonmetal reactivity are in this top right corner. In the bottom left corner, so make some arrows that point down and to the left and write increasing atomic radius and increasing metal reactivity. So our biggest and most reactive elements are down in this corner. Now, on your notes, try some check your learning practice. I'm going to give you some pairs and see if you can figure out who's biggest, who's got the most ionization energy, electronegativity. See if you can get those right, and then I'll see you in class.